All right, good evening, everyone. This is Celso Batalha, Evergreen Valley College. And we are, if we go to modules, on this week modules, January 15 to 19, there are two group discussions going on, start birth and death. And I didn't receive a lot of hits on these um, two discussions. Today I barely had any hits in there. So please start putting your ideas, because the earlier you get, the better chance you have to improve your grades. So I also would like to let all of you know that some of the questions are in midterms are I'm taking straight from the end of chapter questions. So I'm using the seeds in there, certain questions that are given at the end of chapters, and I'll show you some of them. In fact, I have them right here. There you go. This is for the chapter 22. You have these questions. And then what I'm doing is to create questions, multiple choice questions based on them. So if you read the chapter and you visit these questions and try to answer them, it's a way to start thinking ahead about probably materials that I will ask in the exam. Now, I also noticed, and some of you called my attention to, that few questions in midterm number 2 were not addressed in the chapters and sections that I recommended reading. And that is totally possible because I'm using test banks that I used last semester, and I changed the book to OpenStax to allow for free of charge test books and materials, test books and materials. And the problem is, although I did a lot of cleaning, I might have some questions might slip through the cracks. This could happen. And what I did, I gave some extra points to all of you. Assume that you probably got some of these questions. It's not a lot, but you might have gotten a couple or three or so, and then I gave you some extra points on that. It's possible that in midterm number 3 the same might happen. I would try to review over the weekend and try to do some more cleanup, but we never know. Now, there is a makeup exam. The makeup exam has to be done through Proctorio. I will not be face-to-face proctoring at Evergreen, and the reason is the makeup exam is not mandatory. It's something that you do if you want. I recommend you do because it increases your chance to improve your grade. What I do, I take your midterm score, I compare with the lowest score in midterms, and of course I'm talking about the percentages, and then I swap that, okay, and pretty much that's what I do. I don't see what else, and pretty much that's it. So let's talk about stellar evolution. Now, one of the core subjects in stellar evolution is the so-called Hertzsprung-Russell diagram. This diagram is a diagram that relates two quantities, and in the vertical axis of this diagram is luminosity, and in the horizontal axis is temperature. And in some situations or in some diagrams you can see it given as spectral type, going from O stars to M stars. So the chapter we studied spectral classification and spectral type, and we saw the excellent work done by a battalion of women, um, early in the 1900s, they got data for several stars, and they were able to organize that data, spectral data, and group the stars based on similar features found in specific transitions. And nowadays we still carry the labels and the classification they they work on. So the classification is that you need to remember is OBAFGKM. OBA, fine, girl or guy, kiss me. That's a nice way to remember. And O is the hottest type of star. M is the coolest type of star. OBA, fine, girl, kiss me. OBAFKM. FGKM, I forgot the G. So that's how the classification goes. Our sun is somewhere here, is a 6,000 Kelvin star, which is indicated here by this cross. So if you go from the cross and you draw a vertical line to here, you're going to bump in about 5,600, 5,700 Kelvin. That's the surface temperature of our star sun. And if you draw a parallel line towards the vertical axis, 10 to 0 is 1. 1 what? Solar luminosity. That's how this axis is organized. Is a factor, is a power of solar luminosity. So this diagram is interesting because you can play around. You can do the following thing. You can get a star and then you change. See, I'm changing the temperature here. But as you can see, I'm not changing the luminosity. So a star that shares the same luminosity as the sun, see, is the same luminosity as the sun has. Let me go back here. This is a star, and now I'm placing that star exactly in the line where the sun should be located. And just as I recall what we studied yesterday in respect to HR diagram, this line here is the line called main sequence. And the stars that belong to main sequence, like our sun, are stars that are undergoing fusion reactions in their very core. And these fusion reactions are such that 4 atoms of hydrogen are being fused into 1 atom of helium, and then energy is being created, energy is being produced, and that energy is the one responsible for keeping the star in hydrostatic equilibrium. The star does not contract and the star does not expand, and that's why for nice hundreds of millions of years, which is good for us living organisms, the sun has been kept its same size. It doesn't contract, doesn't expand. So it's always the same. So what I would do here in this exercise is, what if I change the position of a hypothetical star in the HR diagram in such a way that its luminosity is the same, but the star has a surface temperature that is slightly less than the sun. In fact, it is a lot. Which temperature I have? 3,500 Kelvin. Let me make it so that its luminosity is still solar. See, solar luminosity about 1 right there. 1. There you go. So this star has the total energy is putting out in the space. This crossing star match that of the sun, but is much cooler. So that much energy to match what the sun produces require the star to be much bigger. And much bigger, I mean what? Well, somewhere with a radius that is between 1 solar radius and 10 solar radius. That's how you are reading the diagram. So for another token, let's say that I want to study a star that is a main sequence, but is very hot. So a main sequence star that is hot, in my case here, I'm placing very much close to 40,000 Kelvin, in fact 34,000 Kelvin. This star is blue, as you can see, and bigger. So in the main sequence, stars that are in the lower right hand side of the HR diagram, they are called M dwarfs. M dwarfs. M because they are cool stars. Dwarfs, as you can see here, because they are much smaller than the sun. We had an extra credit that was based on the finding of an exoplanet orbiting a M dwarf. And what we learned in that extra credit was M dwarfs are very active stars. So these tiny stars, although tiny, they have a lot of convection and they have a lot of magnetic activity. And as astronomers thought that planets orbiting M dwarfs probably wouldn't have an atmosphere. And the reason for that is with activities, solar activity, like the sun becomes active and produce lots of solar wind. This solar wind interacts with our atmosphere and affects weather patterns. So astronomers thought that active M dwarfs, maybe their exoplanet would be deprived of atmosphere because the star activity would pretty much wash out and evaporate any atmosphere that by any chance they would have. And this extra credit article indicate that was not the case. They found a exoplanet around a M dwarf, and that exoplanet show or indicate suggests the presence of an atmosphere. How did they found that? Well, because they observed the M dwarf in two different wavelengths, in two different color bands. And the transparency of the atmosphere depends on which wavelength you are observing. And by observing different wavelengths, they were able to measure different sizes in the atmosphere. And by doing so, they were able to prove the existence of some hazy gas around the exoplanet. And this extra credit article also gives you a hint of how science works. I mean, we know exoplanets exist now, they have been confirmed. So we have some hypotheses. Well, M dwarfs are active and exoplanets might not have atmosphere, so we need to observe. And the observation revealed an atmosphere. So the hypothesis we had was not correct, and then we cast it away. So that's how pretty much science works. But let's go back to the HR diagram. Now, as we study stellar evolution, there is a group of stars called giant stars. So giant stars, red giants, like our sun, when the sun evolves, the sun will become a red giant. It's a star that is cooler than the sun is, which means cooler means redder than the sun, and you can see in this diagram. And giant, which means is bigger than the sun. And eventually this star will undergo some changes. And our book doesn't go in a lot of details on those changes. They are not important. But eventually, once the star ends its pause, means main sequence evolution, and become a planetary nebula, casting away most of its external layers of gas, that core will appear right here as a white dwarf. A white dwarf that is substantially smaller than the sun itself, In fact, can be as big as a planet Earth, which is 100 times less than the sun, but much hotter than Earth. So Earth is not hot at all, right? But these white dwarfs are several tenths of thousands of, of Kelvin of surface temperature, and they are very compact to the point that if gas falls on them, this gas might flashes out in phenomena we call nova. So let's get out of this animation. So if you want to explore this animation, please go on this site, and I have that in Canvas, and then play around and let me know. So these equations here, don't worry about it, but play around with the star itself. You can make them hot or cooler, and then you can. Oh, I forgot to mention the supergiant. So what supergiants are? Supergiants are main sequence that once they exhaust the fuel, the hydrogen they have and they carry in their very core, they move to the right in the HR diagram and they become supergiant. Red supergiant or blue supergiant depend on which fusion reaction is going on in their very core. As we will see today, when the hydrogen in the core is exhausted in these supermassive stars, different types of fusion reactions go on. So you have hydrogen is exhausted, and then you initiate helium fusion reactions, and then carbon fusion reactions that also produce some oxygen, and then neon fusion reactions, and then oxygen fusion reactions, and then silicon, and then finally a core that is primarily iron. And when this iron core is produced, they start the iron cannot be fused into heavier atoms without accepting energy instead of producing, and then iron cannot fuse anymore into heavier atoms. And then what happened is the core collapsed at very high speed, and the star all collapsed towards the core, bounced back, and then we have an explosion that is called and termed supernova. So let's go quickly over these slides just to browse through them, and then I would like to explore the questions we have at the end of this chapter 23. Wait a second, I want to take these things away. It's kind of a bad here. Okay. There you go. What is this? This is a picture of a region where you have it all. So you have, let's see if I can get a power. No, I can do it. Keystone. So I don't have a cursor now. That's why I'm kind of lost here. I would like to have a cursor, and I can. Can I have annotate? I don't think I can. Let me see if I can. See if I can write. No, I cannot. If I try to write anything, I move. Yeah, so I cannot annotate for now. I have to figure out a way to better present slides and take notes as we go. I can do with a PDF, but I have to erase all the time, and that's not working so well as I thought it would. But look at this. You have a picture. In the center of this picture, you have a cluster, an open cluster with stars in the process of formation. But see this fuzziness right here? Oh, I don't have the cursor. This fuzziness at the right of the cluster indicates stars that have been passed away, if you will. They have exploded already. They are supernova. and they already initiate the process of returning gas to the interstellar medium enriched by atoms they formed in their very nuclear part. And in the lower part of this picture, you have gas. And this gas is still there, ready to form clusters of stars or association of stars. So you have it all in this picture. You have stars that have been formed. You have stars that are dying because you can see the gas that is spelled out, and that you can see in these three bluish ghostly images right of the cluster. And in the lower part, you have molecular clouds that might give rise to new groups of stars or association. Now, as I mentioned today and yesterday too, a star like the Sun, or a star that is less massive than 8 solar masses, 8.0 solar masses, which means you take the content of the Sun, a star, Sun, and then you add 8 stars like the Sun together, the same material of 8 stars like our Sun, and then we call that 8 solar mass star. So an 8 solar mass star is considered a low mass star, okay? Whereas high mass stars are those that are 10 solar mass or more than that. Nowadays, we don't think stars that are 100 solar mass can exist without being disrupted. So we think that stars, the majority of them, are low mass stars. That's how galaxies prefer to form stars as we know. And high mass stars, 20 solar masses, 10 solar masses, they are rare. They don't appear so frequently. And also they die quickly. The parameter that controls stellar evolution is mass. More massive stars go through their evolutionary phases much faster than stars that are low mass stars. Okay? So if you have a group of stars being formed at the same time, and right in my left hand side, you have a huge massive star, right? And in the right hand side, you have a cloud of stars that is still formed, much less material in it. So what happened is this massive star that is going to be a star will quickly go through the pre-main sequence phase and become a main sequence in few, sometimes hundred thousands of years, depending on the mass. Whereas a low mass star like the Sun will take 20 million years, not 100,000 years, 20 million years just to go through the process of contracting and becoming a main sequence. Now, once they reach the main sequence, this massive star that is sibling, has the same age as that of the low mass star, this high mass star goes quickly through the main sequence phase and quickly exhausts its fuel of hydrogen in the core, and quickly, in a few hundred thousands of years or so, is out of the main sequence and become a supergiant. Whereas a star like the Sun will take 10 billion years in the main sequence, going through the slow process of converting hydrogen and helium. And then eventually it leaves the main sequence and become a red supergiant. Now, for a low mass star, the post-main sequence phase is the giant phase, and then as an asymptotic giant branch phase, in which the star at that phase has a carbon core, and then eventually it goes through the planetary planetary phase, in which a core that is a white dwarf is surrounded by an expanding gas of 30 kilometers per second or so. And then eventually we have only the white dwarf phase. So a low mass star is what? Main sequence, become a red giant, a horizontal branch star, asymptotic giant branch star, planetary nebula, and then eventually a white dwarf. So those are the typical phase of a low mass star. High mass star, it's the main sequence, and then blue and red supergiant, and you stay navigating in between red and blue, depending on which fusion reactions goes on in the core. Now, low mass star, what was shown by calculations of Chandrasekhar is, I think there is a, yeah, there you go. So Chandrasekhar, he was Indian astronomer. He works with Sir Eddington in Britain, and he calculated what would be the highest possible mass a white dwarf should have without collapsing and exploding in a supernova. And today we know this supernova exists, this explosion exists and have been used to map out our universe and establish proper distances and scales to the entire universe. So what is the supernova type 1 that is so important to establish distance and scale in the universe? So a supernova type 1 is the result of a white dwarf that is in a binary system with a main sequence star. And a white dwarf cannot have a mass, as this diagram show, that is more than 1.4. See this diagram? Mass in solar masses goes from 0, 0.2, 0.4, 0.6, but cannot be more than 1.4 solar masses. This calculation was done by Chandrasekhar. He proved that white dwarfs, if they were more massive than 1.4 solar mass, they would be unstable and they would explode entirely. Now, the explosion and the converting in energy of 1.4 solar mass is an amount of energy, is an amount of luminosity that can be readily calculated. So astronomers then search for supernova type 1 because if they found one supernova type 1, chances are they have a very good chance of establishing a precise distance to the galaxies where this supernova got to be exploded. So this black line, not the red line called main sequence. The main sequence is a line that indicates 90% of the star in the sky. So, but the black line indicates the phase A is the phase where the star is initiate or finalize its asymptotic giant brain phase, and the phase B is when the star is outcasting, is putting out its the shell that overlies the core. So the entire body of the star that is above the core is turning, is flashing out, is spelled out towards the interstellar median. And then when you observe these members, in fact, they are beautiful to see. Let me show you some pictures of planetary nebula. They all have these same characteristics. See, this is the Ring Nebula. They have a central, see this central dot right there, kind of a brightish. Same thing here, see that? Here I can't see over there, but certainly here. Certainly there. So this planetary nebula, in fact, what they are is an expanding gas with a central star that is a white dwarf. This is a white dwarf, which is the core, the region there. Originally, the star was undergoing fusion reactions, right? Hydrogen being fused into helium, and then when these shells expand, that's what you see. You see these beautiful configurations whose morphology is primarily controlled by the star magnetic field. So you don't need to worry about these details, but just to say planetary nebula or represent stage in the evolution of a low mass star like our sun. Our sun will become a planetary nebula once its hydrogen fuel in the core is exhausted. Um, so let's take a look at some of the questions that exist at the end of this chapter. Let me take one, and again, think about these questions as one that I might use to come up with questions for the exam. What is the first event that happens to a star with roughly the mass of our sun that exhausts the hydrogen in its core and stops the generation of energy by the nuclear fusion of hydrogen to helium? Well, this is a long question, but when a star like our sun, the core of it in the very beginning of its main sequence life, it's called zero age main sequence. The core is 75% hydrogen, 25% helium primarily, as well as the rest of the star, not just the core, but the rest of the star. The core certainly is hotter and more dense than the rest of the star. So because of this higher density and higher temperature, fusion reactions take place in the core. It's not in the entire star, just in the core. And then 20% of it, of the star, will be ignited in fusion reactions. And as we saw yesterday or 2 days ago, 4 atoms of hydrogen creates 1 atom of helium and liberates energy. That energy warms up the star, keep the star in hydrostatic equilibrium. But eventually, that hydrogen that is responsible for producing and providing this energy, hydrogen is going to be gone. It's going to be a core primarily of helium atoms. So what happened when this core of helium atoms is achieved, when the ashes of fusion reactions is pretty much done and the core is primarily helium? So what's going to happen? So when that phase occurs, the core itself is surrounded by the rest of the star that is pretty heavy. So the weight of the star crashes the core and forces the core into a smaller volume. So when you compress gas, elements and the not molecules, but the elements, the plasma itself reacts with confinement with mobility. In other words, the temperature, the gas temperature in the core increases substantially. It goes from 20 million Kelvin and grows slowly up to 100 million Kelvin when fusion reactions of helium will take place. But between the point of initiating the contraction towards this 100 million Kelvin, from that point, one important aspect happens, and that is the shell gets to be surrounded by a hydrogen fusion shell. So now if you could picture the core would be a hydrogen fusion shell surrounding a core that is heating up. Now the result in the net of energy, as far as we can tell, is that more energy now comes out of the core. So the star expands. So the star expands, we call that a giant star. But not only that, because the star expands, the outer layers, the molecules that compose most of the atmosphere, they will be separated because of the expansion. So the separation between atoms and molecules increase. Less collision takes place, and collision is translated in physics with temperature. Less collision, less temperature, the star is cooler. And in physics and astronomy, the cooler the gas is, the redder it is. The hotter it is, the bluer it is. So that's going to happen with the core. So the core keeps contracting and heating up. The star, the outer shell, the atmosphere expands and cools down. Eventually, the core will reach the point of density and temperature that will ignite helium fusion reactions, and then carbon will start to be formed in the core of the star. When this moment arrives, the star is said to be a horizontal branch star. It's a star that has a core in which helium is undergoing fusion reactions and the star is somewhat stable because now a constant flow of energy comes out of the core. Now, but all good things come to an end, and eventually these fusion reactions, these helium fusion reactions, will also come to an end because the core is going to be a carbon core. So when the star is reached the point of having a carbon core very dense, and again I'm talking about a low mass star, then the same process will happen. The carbon core will initiate contraction, a helium fusion shell surrounds the core, a hydrogen fusion shell surrounds the helium fusion shell, more energy comes out of the central part of the star expands in what we call AGB, asymptotic giant branch star. And then eventually, all this surplus of energy from the core flashes out and the star expels its outer layers in what we call planetary nebula. The core is revealed, and we call that white dwarf. So number 4 is exactly what I just said. Describe the evolution of a star with a mass similar to that of the sun, from the protostar stage to the time it first becomes a red giant. That's what I just went through. Although I didn't explain the pre-main sequence phase. The pre-main sequence phase means you gotta have gas, cold gas, in the interstellar medium with a certain density that allows the gas to contract. So contraction slowly tends to bring the gas to a point where the star will reside, and we call that protostar. And because there is some initial rotation, and astronomers call that angular momentum, this rotation will flatten the system into a circumstellar disk around the star, and as gas falls towards the star, not necessarily falls directly towards the central star, but falls also towards the circumstellar disk that spirals towards the central star. On which edge of the main sequence in number 7 on an HR diagram would the zero-age main sequence be? On which edge of the main sequence band on an HR diagram would the zero-age main sequence be? I swear I didn't understand the question. The zero-age main sequence is the part of an HR diagram where, let's see if I have here, an HR diagram. There you go. Let me show you the path of a low mass star, the formation of a low mass star. So eventually this low mass star is formed somewhere here. We call that a T-Tauri star. And then the T-Tauri star contracts and eventually becomes a main sequence. So when the star ignites its fusion reaction in the core, it's called zero-age main sequence because it's the starting point of that star in the main sequence. That's what zero-age main sequence be. So let me go back to the question, on which edge of the main sequence band? I don't know what the question means. I would say in the right hand side, right? Because the zero age is somewhere here. and then the star changes slightly position. How do stars typically move through the main sequence band on the HR diagram, and why? So the star doesn't move. The sun is evolving. The sun is changing its luminosity and its surface temperature throughout its life. And as a result of that, the combination of luminosity and temperature will yield different position of the sun in the main sequence, right? Perhaps that's what question number 7 was referring to. So the luminosity change, the sun is slightly more luminous than it was when it initiated its life. Um, and 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 so this changing in position in the HR diagram are not associated with the changing spatial position of the sun. So the sun doesn't move up and down, go north and south. It doesn't do that. The sun is there as it will be in the center of the solar system, more or less. But its size, its luminosity, its surface temperature will change. Number 9, certain stars like Betelgeuse have a lower surface temperature than the sun and yet are more luminous. Why is that? Because Betelgeuse is a huge star. Betelgeuse is a star that should be somewhere here, right? It's a red supergiant. So it is cooler than the sun. The sun is about 6,000 Kelvin. Betelgeuse is I don't quote me. Let me see what's Betelgeuse temperature. Just a second. Betelgeuse. So Betelgeuse is right there, 3,500, right? 3,500. So Betelgeuse is 3,500. And let's see if we can get some information about luminosity. What is this Betelgeuse luminosity? Mass, distance, surface temperature, spectral type. It doesn't, I think I have it here. Let me see in the Starry Night. Betelgeuse is right here. What is the luminosity? Oh, there you go. It's about 60,000 suns. 60,000 suns. So let's go back. 60,000 suns right here. So 60,000, this is 20,000. So pretty much this is Betelgeuse, 60,000 suns. That's where Betelgeuse is. It's a red supergiant. Why is it more luminous? Look at the size. See that? It's a heck of a star. So the sun has one solar radius. So take the size of the sun. It's 100 times bigger than Earth. Look at the Betelgeuse. Is somewhere between 100 times the size of our sun to 1,000 times bigger than the sun, right? So it's a huge star. So Betelgeuse, although if you take 1 square inch of the sun and 1 square inch of Betelgeuse, the square inch of sun is more energetic than the square inch of Betelgeuse. But the area of the sun that is radiating this energy is much smaller than the radiating area Betelgeuse has as it put out energy in space. So Betelgeuse is bigger and then puts out more energy, more luminosity. So it's the size. Size matters in this case. How about number 10? Gravity always tries to collapse the mass of a star towards its center. What mechanism can oppose this gravitational collapse for a star? Is the energy, is radiation that comes out of the core as a result of fusion reactions. This gas pressure produce this outward expansion that counterbalance the pulling effect of gravity. During what stage of a star life would there be a balance between them? Well, there is a balance between contraction and expansion when the star is in the main sequence, and in the case of a low mass star, in the horizontal branch. So the star does not contract, does not expand, remains at about the same size, more or less. But primarily in the main sequence, that's when hydrostatic equilibrium is pretty much preserved. Okay. So I don't want to take more of your time. Sarah, let me just stop taping for now so I can talk with the students that are here. Good night to all of you and see you mañana.